Welcome to Power Supply Review, Full Wave Filtered Rectifier. So here we have our circuit with our transformer and our bridge rectifier, filter cap, and a load resistor. So the first thing we need to do is determine the primary voltage. If that's given in RMS, I like to convert that immediately to peak. Then we need to figure out the secondary voltage. We're going to use the turns ratio of the transformer to calculate this secondary voltage. Now that we have the secondary voltage, we can figure out what Vout max is going to be, or VC max, by subtracting 2 diode drops from the voltage on the secondary, and that's going to be 1.4 volts. And now we need to figure out what Vout min is going to be, and that is essentially going to be the discharge of the capacitor through the load resistor. We're going to use our VC formula to find that voltage, and remember we're calculating for a discharge situation, so our V final is going to be 0. Our V initial is going to be the max voltage that we just calculated, and the discharge time for a full wave rectifier is going to be half of what it was with the half wave. So the frequency coming off the bridge is going to be at 120 hertz. So our time is going to be 1 divided by frequency. And once we have our V min in terms of peak, we can now calculate our V ripple peak to peak by subtracting that V min peak from the V max peak. We know that the VDC is simply the average, the voltage that's right between the V max and the V min, so V max plus V min divided by 2. We know that RMS, we know that essentially that signal is kind of a triangle wave, so we've got V ripple peak to peak divided by 2 times the square root of 3. That gives us our RMS. And then finally, to determine our percent ripple, we've got V RMS divided by VDC times 100.